Okay, Assalamualaikum. So today we continue our lesson on chapter 2 and the subtopic is balance fault. Okay, balance faults. So by the end of this subtopic, students should be able to determine fault current, bus voltages and line currents when balance faults occur in the power system network. Okay, so this is our outline for chapter 2. So we already finished single line diagram, reactance and impedance diagram, per unit system, component representations, steady state approach using per units approach. So today we will focus on balance faults and short circuit capacity. Okay. So faults of power system can be divided into two main categories, which is balance three-phase fault. This A, let's say this A. Okay, type A is balanced three-phase faults. Okay, let's say we have three line, red, yellow, blue, red, yellow, blue. Okay, three-phase fault is faults occurs on these three-phase line, balance faults. Either faults occur on red, yellow, blue, red, yellow, blue, or red, yellow, blue to ground, or grounded faults. Okay, to ground. This is a balanced faults. Another type of faults is unbalanced type of faults. Okay, let's say this B, unbalanced type of faults. For unbalanced type of fault, we can divide this type of fault into three categories. Okay, three subcategories, which is single line to ground faults. Let's say we have red, yellow, blue, single line to ground faults. Either one line is faulted to the ground. Let's say this line faulted to ground. This is single line to ground faults. Okay, this one double line faults or line to line faults. Okay, let's say we have three phase, red, yellow, blue. Either these two lines faults, okay, red, yellow, blue, or yellow to blue faults. Either one. This is line to line faults. Okay, the other type of faults is double line to ground faults. Let's say we have this red, yellow, blue. So these two phases faulted together and then faulted to ground. Okay, okay, this is a double line to ground faults. So we have three subcategories for unbalanced type of faults, which is single line to ground faults. This one, line to line faults. So either red to yellow or yellow to blue. Okay, and another one is double line to ground faults, something like this. Okay, so in this subtopic, we only cover balanced type of fault, which is the faults type number 1, A, three-phase balance fault. Okay, for unbalanced type of faults, this topic will be covered in the power system analysis subject. Okay, this one is quite simple. Type 1, type B is quite complicated. Okay, so we just focus on this type of faults. Okay, life of faults. Life of faults depending on the periods of faults. So we can divide that life of fault into three categories. One is subtransient. Subtransient, usually when fault occurs, current, let's say this current, magnitude of current, this time, duration. When fault occurs, current will increases significantly. Okay, something like this, and then start to stabilize, and then steady state. And this few cycle, we call it as subtransient period. Subtransient. Transient. Okay, only few cycles of faults. Transient duration, maybe 10 of cycles, and after that we call it as a steady state period. Okay, so this is the life of faults. So during a few cycles, the fault current is very high. It's jump very high and then start to dropping for a few cycles, and then after that the fault current reduces during the transient period, and then when the steady state, the fault current will become steady in the magnitude. Okay, so this is the life of faults. Okay. So if we look at the balanced faults, usually the information used from the fault current can be used to select and set a phase relay. Okay, what is the function of phase relay? This phase relay is used to tell the circuit breaker either this magnitudes of current is a fault current, or this is the ordinary type of current or load current. So to differentiate between fault current and ordinary current, relay is being used. Okay, so another one, line to line faults, okay, is used for the ground relay setting. Okay, so in our case we use 3-phase balance fault to set up or phase relay setting. Line to line or line to ground fault we use for ground relay setting, and other type of fault we use for other type of setting. Okay, fault studies are also used to obtain the rating of protective switchgear or circuit breaker. Okay, so we want to select the right size of circuit breaker or switchgear. We have to know what is the maximum or the fault currents magnitudes during the faults. Okay, so the magnitude of fault current depends on the internal impedance of the generator. Okay, so in this case, usually for the generator we have Xg. Okay, this is Xg for steady state. So we have Xg subtransients, Xg double prime, we have Xg transient, and we have Xg steady state. Before this, we only use this Xg, internal impedance for the generator, for the steady state, because we are doing the steady state analysis previously. But for the fault study, sometimes we will use Xg subtransients, this one Xg double prime, or Xg prime, depending on what type of analysis we want to do. Okay, so this is a cause of faults. Okay, sometimes faults occurs because of lightning, heavy winds, trees falling, and so on. Okay, balanced 3-phase faults is a simultaneously short circuit across 3 phases. Okay, generally, subtransient reactance is used to determine the interrupting capacity of the circuit breakers. Okay, so we use subtransient reactance, okay, to determine interrupting capacity of the circuit breakers. If fault studies require for relay setting, transient reactance is used. This is what I said just now. We have, this is Xg double prime, subtransient reactance is used. For the relay setting, we use Xg prime. Okay, this new, this is maybe new for you, because previously we only use Xg for generator, steady state reactance. Okay, steady state reactance. So if fault's impedance is equal to 0, okay, fault impedance equal to 0, let's say this X fault equal to 0, so we call it as a bolted fault, or sometimes we call it as a solid fault. That means X fault is equal to 0. There is no impedance, okay, when the faults occur. Okay, so now we go to fault calculations. So when we want to solve the faults analysis, we have to make some assumptions. Okay, this is a few assumptions we have to make. So first, the EMF of all generators are 1 per unit. Okay, we just assume 1 per unit. Actually, this EMF is depending on the load flow data. Okay, the system voltage is at its nominal value, and the system is operating at no loads at the time of faults. Okay, so we assume 1 per unit. and voltage is at the nominal value operating at no load. Okay. Second, shunt elements of the transformers model that account for magnetizing current and core loss are neglected. So we just ignore the value of shunt elements for the transformer. Third, shunt capacitance of the transmission lines are neglected. Okay. This one also we ignore the shunt capacitance elements for the transmission line. Then fourth, system resistance is neglected and only inductive reactance of the system is taken into account. Okay, so we just consider the value of inductive reactance. So we usually ignore the value of resistance R. We just use XL in our. Go straight to the example. The one line diagram of a 3-bus system is shown. Each generator is represented by an EMF behind the transient reactance. All impedances are in the per units on a 100 MVA base. For simplicity, reactances are neglected. Okay. The following assumptions are made. Okay. Shunt capacitance are neglected and the system is considered on no load. All generators are running at their rated voltage and rated frequency with their EMF in phase. So, determine the fault currents, bus voltages and the line currents during the faults. When a balanced three-phase fault impedance ZF is equal to 0.16 per unit occur on bus 3. So let's say the faults occur here. Okay, three-phase balance faults occur at this bus bar. So find the fault current. So what is the IF? I fault flowing in this line. Bus voltages, we have this bus bar, bus 1, bus 2, and bus 3. So V1, V2, and V3. And the line currents during the fault. This line current, let's say this one, I line current from bus bar 1 to bus bar 2. This one, line current from bus bar 2 to bus bar 3. And then this one, line current I from bus bar 1 to bus bar 3. This is line current flowing in this branch. And then this bus voltage. So we have to calculate fault current, bus voltages and line current. So how to solve this problem? Okay, so this is our circuit. So we have this circuit, we have the generator, okay, we have two transformer, we have the network like this, 3-bus test system, and fault occur at this bus bar. Okay, so the fault at bus 3 is simulated by connecting fault's impedance ZF equal to J 0.16 per unit. So this one. How to find the fault current? Current flowing in this line, I fault. So to start our analysis, we have to consider this network. Okay. And then we have to use Thevenin theorem. So, the fault current at bus bar 3 is equal to this one. V faults, V at this bus bar over Z33, Z Thevenin plus Z faults. Okay. Z Thevenin plus Z faults. So, according to the Thevenin theorem, okay, the change due to the short circuit is equivalent to that caused by the added source Thevenin is equal to VTH. Okay, this one. With all other sources shorted as shown on the right. Okay, so actually here is the generator 1, G1, SG1. This one SG2. Okay, when we use the Thevenin theorem, when faults the Thevenin theorem said that when faults occur, this original network can be replaced by this network by shorting these two generators. Okay, this generator is connected to ground, and then we add another Thevenin at the shorted bus bar. Okay. For this case, the fault is occur at bus 3, so we add Thevenin at bus bar 3. And then we add Z faults at bus bar 3. Okay. This one. Because faults occur here, this bus bar, we just add Z faults at this bus bar. Okay. So from this network, we short these two generators and we add Thevenin, so the network become like this. Okay. So this is our network now. So, and it also says that V3, this one V3 pre-faults is equal to pre-fault voltage at bus bar 3. Thevenin is equal to V3 0. This means V3 pre-fault voltage. And in this case, we consider this pre-fault voltage is equal to 1 per unit. Okay. It is now easy to solve for the changes due to the faults. These changes are then added to the pre-fault values to get the post-fault values. Okay. So now our network become like this. So what we have to do, we have to simplify this network so that it's become Thevenin network. Okay, Thevenin circuit. So what does it mean? So this circuit should be simplified to be like this. Okay, so we have this one plus, minus plus, here is minus, this is plus. So this is fault. So it become like this. This is Thevenin. This fault current. So when this circuit is being simplified by this circuit, we can calculate fault current by using this equation. Okay. So I fault current faults flowing in this bus bar. So I faults equal to Thevenin, or in this case Thevenin is equal to V30. This one, Thevenin equal to V30 over Thevenin plus Z faults. This one Z33 is Thevenin. Okay, looking at this angle. Okay, this is Thevenin. This one is Z fault. So this is the equation to calculate fault current. So how to solve this equation? We have the delta connection over here. So we have to simplify the circuit. How to simplify the circuit? This delta can be transformed into the Y connection. Okay. So we have this delta connection. Okay. We have this delta connection. Okay. This J 0.8, J 0.4, J 0.4. Okay. We have to transform this delta to Y connection. So this Y connection. Okay. Okay, let's say this S1. So I name it as X1, X2, this one X3. So to find X1 equal to J 0.4 times J 0.8 over the summation of all impedance, J 0.4 plus J 0.8 plus J 0.4 equal to J 0.2 per unit. Same goes to x2 and x3. x2, this one x2, j0.8 times j0.4 over the summation of these three impedance. So we will get the same answer, j0.2 for x3, this one x3, 0.4 times 0.4 over 1.6. j0.4 times j0.4 over j1.6.1. Okay. So that's why when we look at this equation, we get this answer. j0.2, j0.2 and j0.1. So from this circuit, we have to simplify this circuit. This one parallel with this, okay, become this value. So j, this one plus this one, so j0.4 times this one plus this one, j0.6 over this one plus this one. Okay, so 0.4 j1, so equal to 0.24. Okay, j 0.24, same as this value. So this one we just add together, j0.24 plus j0.1 become j0.34. This is Z Thevenin, or in this case we call it as Z33, because faults occur at bus bar 3, we call it as Z33. This is V Thevenin, equal to 1 per unit. In this case, ZF is given in the question, j0.16. So from this value we can calculate fault current. So fault current in this network. So fault current IF is equal to V Thevenin. In this case, V Thevenin equal to V3, VTH equal to V3 pre-fault, which is we assume as 1 per unit. Okay, that's why we use 1 per unit. Z33, what we have calculated just now, j0.34, this is Z Thevenin, and ZF is given in question, is given j0.16. So we will get I faults is equal to minus j2 per unit. Okay, this I faults, current flowing in this bus bar is equal to j minus 0.2. Okay, so not due to the assumption made in the statement of the problem, V pre-fault is equal to 1 per unit. Okay, the pre-fault voltage is equal to 1 per unit. So V1 pre-fault equal to V2 pre-fault equal to V3 pre-fault equal to 1 per unit. Okay, so now we want to calculate what is the bus voltages during faults. Okay, so we already calculate fault current, this fault current in the per unit value. So now we want to calculate bus voltages. So to calculate bus voltages, we have to know what is the changes in the bus voltage during faults. Okay, so to find the changes, so this one, changes in this network during faults. What is the changes here, over here? Okay, voltage change here, voltage change V2 and voltage change V3. Okay, so during faults, what is the changes of the bus voltage during faults? To calculate voltage change during faults because of fault current, we have to know what is the current flowing in this branch. So IG1 during faults, this one IG2. Okay, what is the value of IG1 and IG2? That's why in this example we have to calculate IG1. Okay, now we go backward through the circuit to compute the current in the original circuit. First, the current divided into the two parts through the generator 1 and generator 2. Thus, okay, Ig1 is equal to J0.6 over J0.4 plus J0.6 times I force. So, why we have J0.6? Okay, because here this is a circuit just now. Okay, this is Ig1. This one Ig2. So we use the current divider circuit. So to calculate Ig1, we just take this impedance. So Ig1, this total impedance, J0.4 plus J0.2 equal to J0.6 over total of impedance, both branches, here plus here, so equal to J1 per unit, times fault current, IF3. I fault at bus bar 3 lah, I fault in this case. So that's why we got J0.6 over 1, J0.6 over 1 times minus J2 per unit. I fault 3 is minus J2 per unit, so we will get this value. Okay, so we will get this value. We use current divider circuit. Same goes to the Ig2. Okay, so because Ig2 is here, this Ig2, to calculate Ig2, we use current divider by using this impedance. So Ig2, see over here, Ig2 equal to total impedance here, J0.4 over total impedance of two branches, this branch 0.4 plus this branch 0.6 is equal to J1 per unit, 0 times I faults, I3 faults, 3 faults. Okay, so that's why we get this equation. So 0.4 over 1 times minus J2, we will get this value. Okay, so Ig1 and Ig2 is already calculated. So we have to find the changes in bus voltage during faults. Changes for V1 is equal to this impedance at bus 1 times current flowing, okay, towards that bus bar. So let's say we have this one. This is our original circuit. So we have, this is the impedance. Okay, we want to find voltage changes here, V1. This is V1, right? Bus bar 1, so V1. So during the faults, there is a voltage drop because of the fault current of flowing in this branch. So fault current is equal to Ig1 in this case, Ig1. So Ig1 times the impedance here to get the voltage changes. Same goes to here. Voltage changes to V2 equal to Ig2 times J4, J0.4. Okay, here, impedance over here. Okay, so that's why we get this value. Voltage changes at bus bar 1 equal to 0.2 times Ig1. We get this value, 0.24 per unit. Voltage changes for V2 is equal to, this is impedance, this one, J0.4 times Ig2, J0.4 times Ig2, Ig2 is 0 minus 0.8, so we get this value, J0.4 times minus J0.8, we get 0.32. Okay, for bus bar 3, okay, bus bar 3, we have this. Now this is bus bar 3. Okay, this is bus bar 3. So voltage changes in bus bar 3 because of fault current. This bus bar 3 is equal to current flowing here. This is one I3 volts times impedance over here. Okay, so that's why we have this value J0.34 times minus J2. This is I3 volts. So we get this value for voltage changes during faults. Okay, so to find voltage at bus bar 1 during faults is equal to V1 pre-faults minus voltage changes during faults. So V1 fault equal to V1 pre-faults minus voltage changes of V1, which is we already calculate just now. This one. Okay, we will calculate this one. This is changes in bus voltage during faults. Okay, so to get V1 faults, we just V1 pre-fault minus voltage changes during fault, which is 1 per unit minus 0.2. We will get 0.76. For V2 fault during faults is equal to V2 pre-faults, which is 1 per unit minus voltage changes at bus bar 2, which is 0.32. So we will just put 1 per unit minus 0.32 per unit, and then we get 0.68. Same goes to bus bar 3. We have V3 faults equal to V3 pre-faults minus changes of V3. So 1 per unit minus 0.68 equal to 0.32 per unit. So this is bus voltage during faults. Okay, so during faults, this is the bus voltages. Bus bar 1, bus bar 2, bus bar 3. Okay, so last question is calculate the line currents. Okay, if you look at the question, calculates the line current during faults. Okay, calculates the line currents during faults. So line currents, current flowing in this line. So as I mentioned earlier, line current I12 is equal to V1, this line current during faults. I12 during faults is V1 during faults minus V2 during faults over Z12. Okay, same goes to I13 during faults. I13 is V1 minus V3 over Z13. Okay, same as here. Okay, I23 faults, V2 minus V3 over Z23 during fault. So we will get this answer. Okay, that's how we find fault current IF, I3 faults, V faults, which is V1, V2, V3, and line current IXX, line current during faults. Okay, so we already solved this question. Okay, thank you. Okay, short circuit capacity. So SCC in a bus is a measure of the strength of the bus. So the SCC is defined as the product of the magnitudes of the rated bus voltage and the fault currents. Okay, so usually it is used to determine the size of the bus bar and the size of the circuit breaker. Okay. So from the definition, we have for the short circuit MVA at bus K, or SCC, is given by this equation. Short circuit capacity is equal to square root 3 V lines times I lines. This I is fault current, and then unit usually in MVA. So SCC is equal to square root 3 VI MVA. Okay, this is short circuit capacity. So for example, we have this system. The system is initially on no load with the generators operating at their rated voltage with their EMF in phase. The rating of the generators and the transformers and their respective percent reactance are marked on the diagram. Okay, this is the reactances of the transformer, generator, and so on. So all resistance are neglected. The line impedance is J160 ohm. A three-phase balance fault occur at the receiving end of the transmission line through the ZF is equal to J0.1 ohm. Okay, here. Take the base MVA and base voltage at the low voltage of the transformer. Okay, this low voltage of transformer is 30 kV. So determine the short circuit current and the short circuit MVA for this circuit, this system. Okay. If we look at this circuit, G1, so as G1, we have the 60 MVA rating. G2, we have 40 MVA rating. So this per unit value is old per unit value. So we have to change this old per unit value into the new per unit values. Okay, which based on the 100 MVA. So what we have to do? Let's say this is our circuit. We have the generator. Okay, this is generator 1, generator 2. We have transformer. Then we have transmission line, and then we have this bus bar. So this is G1, this G2, this XT1, this transmission line TL. Okay, so we have to calculate new per unit value for SG1, SG2, ST1, and STL. Okay, we start with the XG1. XG1 is equal to J0.24 times 100 MVA. This is new rating. S base new, S base old, S per generator. This G1 60 MVA, G2 40 MVA. So we go here. So G1 is 60 MVA, 60 MVA times V base old, V base old. In this case, our V base old is equal to 30 MVA, 30 kV, sorry, 30 kV over 30 kV square. So we can cancel it out. So this one we will get J0.4 per unit. Okay. Same goes to SG2. We have J0.24 times S base new 100 MVA, S base old 40 MVA times SG2. SG2 also 30 kV. We refer to the low voltage side. 30 kV. This one also 30 kV square. So we can cancel it out. So we will get J 0.6 per unit. Okay. Then what else? ST1. ST1 is called J0.16. J0.16 times S base new is 100 MVA. S base old transformer rating is also 100 MVA times voltage. Voltage referring to the low voltage side, 30 kV. This one also new voltage is 30 kV square. So because this is the same value, we can cancel it out. So we will get the same value, J0.16 per unit. Okay. So what else we have for the transmission line? The transmission line is 160 ohm. So this is the real value. We have to convert this real value into the per unit value. So we have XTL equal to J 160 ohm. So this actual, we want to find XTL per unit equal to XTL actual over Z base. Okay, this one actual. So how to calculate Z base? So to calculate Z base, okay, so we use Z base equal to V base square, V base square over S base. So voltage level at the transmission line. So voltage level at the transmission line is 400 kV. So V base new. Okay. So square over S base. S base is 100 MVA. So we will get 1600 ohms. Okay. So Z base for this is 1600 ohms. Okay. So XTL at transmission line per unit is equal to J 160 ohm over Z base 1600 ohms. So we will get J 0.1 per unit. Okay. So we have changed all the old per unit into the new per unit values. So from the circuit, to calculate the fault current, we used Thevenin theorem. Okay. So we short all the sources. This is generator. We short all the generators. So we just use SG1. So and then we short another generator at generator 2. So this XG2. And then we have transformer. And then we have transmission line. Okay. This is bus bar. And then we add Thevenin voltage over here. And then over here we have fault impedance. Okay, fault impedance. So we have VTH, this is Z faults. Okay, so this one XTL, this one this one XT1, this one XTL. Okay, so this is our circuit. So SG1 we have the value for SG1, SG2, XT1, XTL, and ZF. So this circuit can be simplified to become like this. Okay, we have one impedance, this XT1, this one XTL minus plus VTH, and then Z faults. Okay, so this one is parallel between XG1 and XG2. XG1 we have J0.4, this one J0.4, this one J0.6, this one J0.16, this one J0.1. Okay, J0.1. So this SG1 and SG2 is parallel, so we can find parallel value for this one, for these two. So we will get J0.24, okay, per unit. So this one is remain J0.16, J0.1, this one J0.1. So we simplify this circuit to become like this. Okay, we want to have this circuit only, minus plus, okay, VTH, ini ZTH with this Z fault impedance, okay, which is J0.1. So ZTH, we just combine this 0.24, J0.16, J0.1. So when we combine all this together, we will get J0.5. So J0.5. Okay. So to find the fault current, we have J0.5, J0.1. find a fault current. Okay, so I faults, let's say I bus bar 3, let's say bus bar 3 fault, I faults is equal to V Thevenin or V faults over Z Thevenin plus Z faults. Okay, in this case we assume V Thevenin is equal to 1 per unit over ZTH, in our case is 0.5 plus Z faults is given J 0.1 per unit. So we will get the fault current is equal to minus J 1.6667 per unit. Okay, so now we solve the fault current. This is in the per unit value. So how to convert the fault current into the actual fault current? So I3 faults actual equal to I3 faults per unit times I base. Okay, so how to calculate I base? So I base equal to S base over square root 3 V base. Okay, so in this case S base is 100 MVA, so square root 3 V base at this region 3, okay, is equal to 400 kV kilovolts. Okay, so based on this we will get the fault, and the base current is equal to 144.3376 ampere. So I3 faults actual equal to minus J 1.6667 times 144.3376 equal to minus J 240.5675 ampere. So this is the actual value of the fault current. Okay, 240.5675. Okay, so minus J. So next question is to find the short circuit capacity. So as we know, the short circuit capacity is given by this equation. Is given by square root 3 of V line I line or faults MVA. So in this case, square root 3 V line is 400 kV, I faults is 240.5674. Okay, minus J. Minus J, that means minus 90 degree. Okay, 166.67 MVA. So this is the short circuit capacity for this bus bar. Okay, so this is the answer.